5, difference of two squares. I'm going to talk about what that means with the two squares. First of all, we're going to be continuing to multiply binomials, so we will be using FOIL again. First, let me talk about what it means when I say a square. By square, think about if we did, for example, 3 squared. We'd get 9. Or 5 squared, 25. 10 squared, 100. A squared, well, A squared, we don't know what it is. The idea with this is that these numbers here, these are what we call perfect squares. They are the result, perfect squares, the result of squaring something, of doing something times itself, right? Which is what it means when we square something, right? Power of 2, that number times itself twice. So when we're talking about difference of two squares, we're talking about you're going to be looking for numbers that are the perfect square of something that was multiplied by itself. For example, if I said 64, what is this the perfect square of? What was multiplied by itself to get that, Vincent? 8 squared, right? 64 is the perfect square of 8. So when I'm talking about perfect squares, I'm talking about these numbers that result from squaring something. Now, what we've got today is the first of a couple different special patterns we're going to be looking at. Here's the pattern. I'm going to show you first with variables, and then we're going to do some examples. If you are multiplying two binomials that have the exact same numbers inside, except one has an addition sign and one has a subtraction sign, right? So this is the pattern. The numbers would be exactly the same. A and A represent the same number. B, B, that represents the same number. So it's exactly the same, except one's a plus and one's a minus. The pattern for this is that your answer will not be a trinomial. Your answer will end up being just two things. Always difference, right? Notice the title of this is the difference of two squares. Difference means subtraction. These are both the perfect squares of whatever A was and whatever B was. Now with just variables that may not make much sense. So let me show you an example with numbers and variables. Let's say we have x plus 3, x minus 3. First underneath here, let me show you what you get if you did FOIL. And then I'll show you the shortcut you can take. If you recognize, hey, this has the same exact contents, but one's a plus and one's a minus, then you don't need to FOIL. FOIL will work, but you could also just follow this pattern. So first let's try FOILing it. If I do first, that's x times x, x squared. Outer, x times -3, -3x. Inner, positive 3 times x, positive 3x. Last, positive 3 times -3 makes -9. Just like yesterday, when you FOIL, your O and your I multiplication should give you like terms. What happens when I combine -3x and positive 3x? Brian? It becomes 0, and we don't need the 0. Essentially, they cancel each other out. And look at what's left. X squared minus 9. You can FOIL these, and it will work. You will get to the right answer. However, if we look at it and try to do it by just following the pattern, if you recognize when you look at these two binomials, hey, this is that special pattern, the same thing except opposite signs, one plus and one minus, the answer is going to look like this. A is this first thing, and my answer says a squared. Okay, so if A is x, x squared. I square whatever's in the A position, there it is. It's always going to be a minus, always. B squared, okay, well 3 is in my B position. What if I square the 3? 3 squared, 9. There's my answer. Because of the opposite signs, the middle two terms will always cancel each other out in this pattern. Let's do one more, and then I'm going to show you why you will need to know the pattern because we're going to go backwards with it. Let me do one more. 2n plus 5, 2n minus 5. Let's try to use the pattern here. We can FOIL it, but I want you to try using the pattern as well. Okay, we see I've got the same exact thing in the parentheses except one's a plus and one's a minus. Which term is my A according to the pattern? Daniel?
2n.
2n. Okay, so the pattern says the first resulting part of the answer will be a squared. What happens when I do 2n times itself? What do I get? Pammy? Right? Think about it. 2n times 2n. 2 times 2 is 4. N times n squared. Okay, it's always a minus. What's my b value in this problem? What term represents b, Izzy? The 5, and the pattern says I need to square that. 5 squared. Done. If you had FOILed it, first, 2n times 2n, 4n squared, outer, negative 10n, inner, positive 10n, last, 5 times negative 5, negative 25, these would cancel out, 4 squared minus 25, 4n squared minus 25. Should I do another one? Maybe one more? Let's do one more. And then I'm going to show you how we're going to go backwards with it. Okay, let's try, let's make it one step, we're going to add in one extra variable. 2a plus 9b, 2a minus 9b. Now the pattern again says take the a value, that's the first one, square it. Take the second value, the b value, and square it, and put a minus in between. And it will always be a minus, because if you take a look back up here at this orange one, when we do last, positive times negative always makes a negative, so you'll always have a minus. Okay, a squared. Here's my a, the 2a. What happens if I square it? 2a times 2a?
4a squared.
4a squared. My b value, 9b. What happens if I square it? We're multiplying it by itself. Roland?
2a squared.
Oop. Not the a. And don't forget, Roland, on that first one, 2 times 2 gives us 4 also. So 4a squared. For the b value, though, what do I get when I square 9b times 9b? 81b squared. Now, notice what happens in our answers here. All of the variables are a perfect square. A squared is the perfect square of a times a. B squared is the perfect square of b times b. All the numbers are perfect squares. Oh, 81 is the perfect square of 9 times 9. 25 is the perfect square of 5 times 5. 4 is the perfect square of 2 times 2. They are all perfect squares. And here's why that's important. Because now we're going to go backwards. Now, what I'm going to do here, I'm going to fold this so we can just see the formula. Here is the pattern. Now, what if we start with this? What if instead of me giving you two binomials, what if I give you something that looks like this? And I say, factor this. Factor means what two things multiply to make this binomial? Now, unlike our previous factoring, there's nothing that I can take out of both of these. There's no number, there's no variable that I could divide out. So for this, when I factor it, I'm doing this pattern. I just flip-flopped it. So if x squared is this piece, all we have to think is what times what times itself gave me x squared? Daniel?
So x and 10.
No, x just, oh, okay, you're getting ahead, you're getting to the next part. What times itself made x squared? X times x, right? What times itself made 100? Daniel just told us, 10. Now, what signs go in here? Well, one gets a plus and one gets a minus. Done, we factored it. I'll do another one in a second. It doesn't matter which one gets a plus and which one gets a minus. We can multiply in any order. My habit is I always put the plus first and the minus second, but it doesn't matter. Let's do another one. What if I say, let's make this one a little harder, 64 y squared minus z to the fourth. Factor it. Now, I am telling you today that these are perfect squares. In the future, you're going to need to be able to go, hey, that looks like the difference of two squares. 64 is a perfect square, y is a perfect square, z to the fourth is a perfect square. Any exponent that's an even power is a perfect square. So again, I've got this side of it here, the a squared minus b squared is what I'm starting with. I'm going back to this. What times itself makes 64? Brian? 8 times 8. Now, don't forget the y squared. What times itself makes y squared? Jaden? Y times y. So that means my a term that I multiplied to get this, 8y times 8y. Okay, z to the fourth. What times itself makes z to the fourth? Diego?
Z to the power of 2.
Yep. One gets a plus, one gets a minus. We factored it. Daniel?
Does it matter which order z squared plus 8y matters?
Yes. Whatever comes first here needs to be the first one here. Because if you notice here, my 8y's are both positive. The z's are the ones that get positive times negative is how I got the negative. So keep it in the order that it's in. Okay, good question. Anybody want me to do one more, or do you think you get it?
Got it.
You guys got it? All right, good. This, if you want me to do another one, you can come on up. I'll show you one.